In this module, we will study about Huckel molecular orbital theory, which is a very important theory in quantum mechanics. Now, first of all, the question which arises in one's mind is as to what this theory is all about and how does it achieve the corresponding objective. As you all know, in quantum mechanics, the fundamental equation is time-independent Schrödinger equation, that is h cap psi equals E psi. If one is able to solve this equation, then from the solution of this equation, one gets two things. One is the wave function psi, and then second thing is the corresponding energy E. This wave function psi is the storehouse of information for the system under consideration, and most of the information about the system can be obtained from this wave function. And there is a wave function, and corresponding to wave function there is energy. That is why we also called energy state and the corresponding wave function. So now this is basically what Schrödinger equation ultimately aims to achieve. But now the bigger problem is that it becomes very difficult to solve this Schrödinger equation exactly. As you have already studied earlier, that Schrödinger equation can be solved only for some small systems, simple systems such as particle in a box, harmonic oscillator, and rigid rotator. These are the systems which we have already studied. And amongst the chemical systems, we can study simple hydrogen atom or one electron systems. You can study, for example, helium ion also. But beyond that, it becomes difficult to solve Schrödinger equation. And therefore, as you have also studied, one uses approximate methods to solve this Schrödinger equation. Amongst the various approximate methods which are used in quantum mechanics, the two most common are perturbation method and secondly variation method. Both these methods and their applications you have already studied in the earlier modules. Now the question comes, what is this Huckel molecular orbital theory? First of all, let me tell you that Huckel was the scientist who developed this theory sometimes in 1930s. He is a very famous scientist who is known for his contributions not only for developing Huckel molecular orbital theory, which we also called HMO, but also he has been instrumental in developing Debye-Huckel theory of electrolytic solutions. This is the theory which one studies in electrochemistry. Now, having said that, this HMO basically is an attempt to solve Schrödinger equation for organic conjugated molecules. So, Huckel molecular orbital theory basically helps us to find out the electronic structure of organic conjugated molecules. Now the question is, why does it apply only to organic conjugated molecules? And why not to other systems? And secondly, how does it operate? These are some of the things which we will study in this module. HMO applies only to organic conjugated molecules. Now, what is an organic conjugated molecule? You all know that an organic conjugated molecule will contain sp2 hybridized carbon atoms. That means it has alternate single and double bonds. If you look at some examples of organic conjugated molecules, the simplest is ethylene. In ethylene, both carbon atoms are sp2 hybridized and there is only one double bond. But if we go to butadiene, which contains 4 carbon atoms, each one of which is sp2 hybridized, and there is an alternate double, single, double bond in this. As a matter of fact, these pi electrons in butadiene are totally delocalized, and because of which all bonds in butadiene are of almost equal length. So such systems are organic conjugated molecules, and it is to such systems that HMO theory really applies. Now there can be a next question, that what is the justification that only organic conjugated molecules are treated in this way? As I just mentioned, that there are pi electrons in organic conjugated molecules, because each carbon is sp2 hybridized, so one electron is in the p orbital and the rest of the electrons are sigma electrons. So each pi electron or a carbon atom ultimately creates a pi electron cloud over the entire molecule, and this is in a plane which is perpendicular to the plane of the molecule. In butadiene, for example, there are 4 sp2 hybridized carbon atoms, and so there are 4 pi electrons. These 4 pi electrons, which ultimately create a pi electron cloud, move in a plane which is perpendicular to the plane of the molecule. If we assume the molecule to be in xy plane, then this pi electron cloud is moving in the z plane. So that is the characteristic of organic conjugated molecules. Extending the same thing, we can say, and you know it very well, that in benzene also there are 6 pi electrons and there is a pi electron cloud at right angles or at perpendicular to the plane of the molecule. So now the question comes, what makes these organic conjugated molecules so special? Huckel thought that basically in these organic conjugated molecules, the properties are primarily determined by these pi electrons. These pi electrons are more polarizable, they can be very easily distorted, and therefore these are the main determinants in the electronic properties. And these pi electrons are moving in a field of the nuclei as well as sigma electrons, which are in the plane of the molecule. So the basis of HMO is pi sigma separability. That means pi electrons can be treated separately, and that is really the entire principle on which HMO theory is based. One additional advantage of this is that it simplifies the problem as well. For example, in ethylene, there are 2 carbon atoms and the total number of electrons is, you can see, 6 into 2, 12 plus 2, 14 electrons. But then there are only 2 pi electrons. See, another beauty of the HMO is that it simplifies the problem. For example, due to sigma pi separability in ethylene molecule, though there are total number of 16 electrons, but in HMO we treat it as 2 pi electron problem. So the 16 electron problem reduces to 2 electron problem. Similarly, in butadiene, if you calculate the total number of electrons, the total number of electrons is 30, but then there are only 4 sp2 hybridized carbon atoms, each contributing 1 pi electron. Therefore, this 30 electron problem is reduced to 4 electron problem. So this is a very big advantage of the HMO. So now we have studied the principle of HMO, and we have seen that it's basically based on pi sigma electron separability, and that it simplifies the problem considerably. Now we come to the next part, and that is how does HMO operate, and that is what we will be studying now. As regards the operation of HMO, HMO basically uses variation method to study organic conjugated molecules. As you have already studied in earlier modules relating to variation method, that in the variation method, one starts with a trial wave function, which is an approximate wave function. And using that approximate wave functions, one calculates the approximate energy. That's basically what we do. And that approximate energy is always more than the exact energy. So extending the same thing here, Huckel used variation method to study organic conjugated molecules. But then the question comes that in organic conjugated molecules, how will we use the trial wave function, or how we will construct or guess a wave function? For this, Huckel used linear combination of atomic orbitals MO method, LCAO-MO. This you have already studied. So he used this principle of LCAO to construct pi molecular orbitals in the Huckel molecular orbital theory. Now, while constructing this, now what are the atomic orbitals to be used in LCO? The atomic orbitals will be the corresponding 2p pi orbitals which are there representing the pi electrons. So that is basically how he started with the trial wave function. In the variation method, as you all know, that if the trial wave function is expressed in the following way as a linear combination of some wave functions, as you can see here, phi a is equal to summation a n psi n. So these are the various linear combinations, and a's are the corresponding variational parameters. And if this wave function is used in the variation theorem, one on its solution gets the corresponding secular determinant. And secular determinant's general form, as you can see from this equation, is H11 minus ES11. It goes up to H1n minus ES1n, and that is the first row. And the last row would be Hn1 minus ESN1, and this goes up to Hnn minus ESNn, and that's equal to 0. That's basically the secular determinant we get. In this secular determinant, as you can see, and you have learnt it already, that Hii will be integral psi I h cap psi I d tau. This is the corresponding Hii, and the Hij would be integral psi I h cap psi j d tau. And there are corresponding overlap integrals Sii, which will be psi I integral d tau, and Sij would be psi I star psi j d tau. So these are the basically integrals which are correspondingly shown in the secular determinant, and this we have already studied. Now the same thing is applied in the HMO. Only thing is that instead of psi n's, which we have written here in phi a, here we have the atomic orbitals to be the corresponding 2p orbitals, as you can see here. Therefore, you know, if we apply it to an conjugated molecule, then the corresponding trial wave function will be the linear combination of 2pz pi orbitals, because we are assuming the molecule to be in the xy plane, and therefore this pi orbital would be in the z plane. Now this wave function can be written as you can see here, phi a can be written as a linear combination of psi 2pzi. These are the pi orbitals which are in the z plane. Therefore, the corresponding expression using LCAO would be for phi a is equal to Ci psi 2pzi summation is over n sp2 hybridized carbon atoms. So that's basically the trial wave function which we use in HMO. Once this trial wave function is used, and then we have the corresponding secular determinant. What will be the size of the secular determinant? That will depend upon the number of conjugated carbon atoms. For example, in the case of ethylene molecule, as you can see here, the secular determinant will be of this form: H11 minus ES11, H12 minus ES12, and the second row would be H21 minus ES21, then H22 minus ES22, and then C1 and C2. So this is basically equal to 0. So that's basically what we get, a secular determinant of order 2 by 2 for ethylene molecule. Now the main question comes, how to solve the secular determinant? To solve this secular determinant, Huckel used the corresponding integrals which come in the secular determinant as the parameters which can be evaluated experimentally. That's why this method is also called a semi-empirical method. Now if you look at these integrals, the integral Hij, if you look at it, if it is I is equal to j, then this integral becomes alpha. This is called a Coulomb integral. And if Hij, I is not equal to j, then it is called beta, which is a resonance integral. It's given the name resonance integral. So these two are very, very important integrals, and their values are calculated by fitting the theory into experimental results. One may also ask as to what is the physical significance of the integral like H11 or H22. These basically refers to the energy of an electron in the field of nuclei and sigma electrons. For example, Hii would mean the energy of the ith electron in the field of the sigma electrons and the nuclei. So this is a very important physical significance of Coulomb integral. Please note that the Coulomb integrals for all the sp2 hybridized carbon atoms in an organic conjugated molecule are assumed to be same. Although this may be a little bit an approximation, because environment of each carbon atom may be slightly different, but this is one of the approximations of HMO, that all alphas, that means the Coulomb integrals, are assumed to be the same for all conjugated carbon atoms. Now we look at the resonance integral Hij. As you see, Hij represents resonance integral, and this detailed form of this is, it is the integral psi I, then you have h cap psi j d tau. So this is basically the energy of an electron in the space or in the region where the two wave functions psi I and psi j overlap. So that's basically the significance of Hij. Now please remember, whether it is Hij or whether it is Hji, both will have the same value. That means both represent the energy of an electron in the region of space where the two wave functions psi I and psi j overlap. This is very, very important. The resonance integral beta, which corresponds to Hij, as you can see from the integral, this represents the energy of the electron in the region of space where the wave functions psi I and psi j overlap. Please note one thing which is very, very important, that Hij and Hji will have the same values, and that will be beta, but this is true only if I and j are bonded to each other. If they are not bonded to each other, then the corresponding integral is assumed to be 0. For example, there is suppose a carbon atom 1 and a carbon atom 4, they are not bonded to each other, then the correspondingly H14 will be 0. So this is a very important thing which needs to be kept in mind. Having considered HII and HIJ, now we consider the integrals SII and Sij. Please note here that Sij in general refers to psi I star psi j d tau. In the case of Sii, it will become psi I star psi I d tau. Now, if it is Sii, then in that case, the correspondingly overlap integral is assumed to be 1. This is so because the correspondingly atomic orbitals are normalized. But if on the other hand Sij is there, then Sij, which corresponds to the overlap between the two atomic orbitals on two different atoms, that is always assumed to be 0. That is, Sij will always be taken as 0. Now, after having considered the significance of HII, Hij, Sii and Sij and their corresponding values, let us try to simplify the secular determinant for ethylene molecule. Ethylene molecule, as you can see, has the secular determinant which looks like this: H11 minus ES11, then we have H12 minus ES12, and the second row is H21 minus ES21, and the last element is H22 minus ES22. Now, if we substitute in this determinant the values of Coulomb and resonance integral, then this secular determinant reduces to a simple form which looks like the following. As you can see that if in this secular determinant we put the values of the Coulomb and resonance integrals, then this secular determinant reduces to the following form. The first row becomes alpha 1 minus E, then beta 1 2, and the second row becomes beta 1 2 and alpha 2 minus E. Please note here that alpha 1 here represents the corresponding Coulomb integral H11, whereas alpha 2 represent the Coulomb integral H22. In reality, both of them are assumed to be same, and therefore, as you will see later on, we will put them equal to alpha. Similarly, beta 1, 2, if 1 and 2 they are connected, then that will be taken as beta. So beta 1, 2 will be the same as beta 2, 1, and that will also be further simplified. Now, on similar lines, if we extend the system arising from 3 p orbitals, suppose there are 3 p orbitals and there is a system containing 3 conjugated carbon atoms, then we will have a secular determinant which will look like the following. Extending our studies, if we now consider an organic conjugated system containing 3 conjugated carbon atoms, that means it would be cyclopropene, then in that case the corresponding secular determinant would be looking as it is shown here. Here you can see that H11 minus ES11 is the first term, then we have H12 minus ES12, and then the third term is H13 minus ES13, and the last row in this would be H31 minus ES31, then H32 minus ES32, and then H33 minus ES33. That is the general form of the secular determinant. Now, if we look at this cyclic system and try to substitute the values, then the secular determinant, after substituting the values of Coulomb and resonance integrals, becomes like the following. It becomes, the first row becomes alpha 1 1 minus E, then becomes beta 1 2, and then we have beta 1 3. Here it is important to note that being a cyclic system, carbon atom 1 is connected both to 2 as well as to 3. Therefore, beta 1 3 is not taken to be 0. It will have a specific value. Similarly, for the rest of the systems, if they are connected directly to each other. And therefore, here the secular determinant looks as it is shown here. So this is how the secular determinant is written using HMO theory. After having simplified the secular determinant, the next step would be to solve this. And if the secular determinant is of order n by n, then on expansion it will give you a polynomial equation of order n. And its solution will give us n energy values and the corresponding n pi molecular orbitals which we will obtain. So that's basically the whole gist of the HMO. Basically, it is a semi-empirical theory which is applicable only to organic conjugated systems, and we write a secular determinant, we simplify the secular determinant, and on its solution we get n energy values and the corresponding n pi molecular orbitals. So to summarize what we have learned in HMO theory today, please note that HMO is a semi-empirical theory which gives a qualitative picture of pi electron systems. This theory treats pi electrons separately from sigma electrons. So sigma pi electron separability is the basis of this theory. And HMO calculations, as you have seen, they are basically carried out using variation method and the approximation of LCAO-MO. This is the basis of the trial wave function which we use in this method. And please see that we assume in this method that pi electrons are moving in a field generated of sigma electrons and the nuclei, and that the corresponding Coulomb and the resonance integrals which we talked about, basically alpha and beta, those can be evaluated empirically by fitting the theory to experimental results. In our next module, we will study about the detailed application of what we have learned about HMO theory in this module. We will apply it to ethylene molecule and to some other organic conjugated systems.